standalone slide, we talked about, we said that if anything's moving, if it's moving in a circle, it must be accelerating because it keeps changing its direction, right? Now, we're familiar with the idea of people in the International Space Station. How many people have seen like videos where they're floating around, that sort of thing? So this is kind of talking about those people. So in order to be inserted into orbit, what they did basically was to, well, first they had to leave Earth's gravity. We'll be talking about escape velocity, okay? But they had to have a certain, well, they didn't leave Earth's gravity, sorry. They had to get in, they had to get a certain ways away from the Earth, okay? And then basically they had, you kind of see how this guy went, this is weird to climb a tower like this, and he actually went ahead and climbed a tower and he set himself out, we went that way, okay? So the thing about it is if he's going this way, that's fine, but gravity's going to try to pull him down, okay? So he's going this way, gravity pulls him down, and he's going this way, gravity pulls him down, and it's, we say he kind of misses the Earth. So instead of falling to the Earth, he continues to go this way. So it's kind of a series of, he's going this way, gravity's pulling him down. He's going this way, gravity's pulling him down. He's going this way, gravity's pulling him down, okay? So it's kind of like, in other words, they call it, basically he's kind of falling to the Earth as he's orbiting the Earth. The free fall is the falling to the Earth part. The fact that he doesn't fall is that because he kind of had a little bit of momentum to kind of insert him into orbit. So in other words, you know, when we see those astronauts kind of floating around, you're like, oh, there's no gravity holding them down. Well, yeah, actually, they're scary enough. Their International Space Station is continually free falling to the Earth. But the reason it doesn't crash on the Earth is because it has a trajectory kind of at a right angle to where it's going to fall. So that's how that works. Okay. So anyway, all right. So in physical science, in this universe, it's kind of nice what there is. There's a lot of conservation laws, okay? So matter cannot be created or destroyed. Energy cannot be created or destroyed, although matter and energy can be converted between each other, okay? But we have a lot of conservation of stuff. It's kind of nice. It's not like our universe is a magician and just suddenly something appears. Okay, it didn't come from nothing. So that's one fundamental law of our universe. I'll just let you know in case I haven't mentioned it before. I think I did. When we talked about our universe getting larger, I think there could be other universes out there, personally. They're called multiverses. So everything has to be conserved. We're going to talk a little bit about energy. Energy has to be conserved. So you can almost see it as something is spinning. Does it seem like it has energy? It has energy, okay? And we can take that a step further. If something is orbiting, it also has energy, and that energy has to be conserved. That energy actually is kind of balled up in something called angular momentum. We talked about momentum before. We said that which has more momentum, a truck going at 30 miles per hour or a bike going at 30 miles per hour? The truck. The truck has more momentum. Now this is angular momentum related to either something twisting, spinning, or something orbiting, kind of that curvature thing. So basically it has to do with how massive is that object, how fast is it spinning, and now we have something else, kind of how far out its mass is distributed. That's the R term, that's the radius term. So does this make sense that what happens if we, well, let's put it this way. I'm switching gears from review to this. Okay, so this always has to stay the same. Angular momentum is conserved, okay? So do you see that if we take the radius and we make it go down, okay, and the mass has to stay the same, the only thing that can change is the velocity. What do you think? If the radius goes down, what does the velocity have to do in order to keep the angular momentum the same? It has to go up. Velocity has to go up, exactly. Okay, so if the radius goes down, velocity goes up. Perfect. So you may not be, this doesn't do it for me as much over here, conservation of angular momentum, but this spinner, this gal on the skates, this really does it for me. If you've done, you've probably seen a figure skater out there, and what happens if she's twirling and she brings her arms in? She goes faster. And so the R thing we're saying is she's basically taking her mass, which her arms are part of her mass, and she's making herself, her R smaller. She's decreasing her R, okay, which you told me would increase the velocity. Okay. Yeah. And I guess this is which law, we talked about this in review session, which law is it of Kepler? He only had 3. Which law is it of Kepler that says that the planets go fastest? When do they go fastest? At perihelion. Yeah, which law is that? I'm thinking, put up fingers, what do you think it is? I'm thinking 2. She looks pretty convinced back there. I'm liking 2 for it. Yeah. They go fastest at perihelion and slowest out there. Okay. And so you figure it's the whole R thing, right? Here, our radius if we're going to the sun as our radius, is smaller, so we go faster. Here, our radius is larger, so we go more slowly. All right. Oh, that says 3rd law, doesn't it? Yeah, well, it should be. Oh, well, I guess it could be, because what else did we say? Okay, I'm switching planets. It could be either one. Very good, very good. Because we said Earth and Mars, who goes fastest? Earth. Yep. And so there we go. That's where the V is smaller too, and it's going faster. Okay, Mars, the V is larger, it's going more slowly. So either one. Yeah. Okay. So energy's got to be conserved. You can track it. Sometimes it's hard to see it and track it. Now, units of energy, we get energy from a candy bar, and of course on the back of the candy bar they say calories, so it's kind of cool. That's like chemical, what our body can do with it. But in the metric system we use units of joules, okay, as units of energy. So, there's kinetic and potential energy. Kinetic is energy associated with motion. Sometimes there's motion where you don't necessarily know there's motion. Okay, and a lot of times a simple formula for kinetic energy, you might have seen this if you've kind of dabbled in, KE stands for kinetic energy. You take 1/2 times the mass times the velocity it's going and you square it. KE is equal to 1/2 mv squared. Energy associated with motion. So what happens to kinetic energy if you increase the mass? It increases. Very good. What happens to it if you decrease kinetic energy if you decrease the velocity? It decreases. Yeah. Very good. Okay. So kind of yin and yang, we have the term kinetic energy and then energy associated with motion, and potential energy associated with non-motion, basically. Potential energy, if you have the potential to do something, then it means you can do it. So potential energy is stored energy. So here, the example of potential energy, how is gasoline potential energy?
Chemical.
It's chemical, yeah. It has the potential to make your car go, but as it's sitting in your tank, it's just like on the shelf. It's potential energy. Very good. And then we have radiative energy. And I was looking ahead to Chapter 5. Chapter 5 is so cool. Chapter 5, we're going to get out telescopes because we're going to kind of look a little bit about how they work. But telescopes, of course, bring light in and they focus. Light is a type of radiation. Okay, you're like, oh, I got radiated. Well, yeah, you know. Okay. So radiation coming from the sun, okay, in all sorts of different forms, including visible light. All right, what else do I have? Oh, I guess that's it. And those aren't the only types of energy, but just kind of hitting some highlights. Kinetic, potential, and radiative. So one of the things kind of setting the stage for talking about the formation of our solar system, basically, is all matter is in motion. And did I mention that? No, I mentioned that during the review session. All matter's in motion, okay? I know it doesn't look like the atoms that are making up this table are in motion, but they are, okay? And if we were to heat any matter, what happens to the motion, you think?
It increases.
It increases, exactly. And so that's kind of what's being shown in these two boxes. How can you tell that this motion is increased over here? Because, yeah, how's it showing more motion? The arrows are longer, exactly. So it's kind of showing you matter over here in motion, you heat it up, it goes even faster. Well, what happens if you cool matter down? It goes slower. Exactly. So I told you the formula to calculate KE is 1/2 mv squared. So you have to square the velocity. So we would say this has more kinetic energy, right? Less kinetic energy. Energy always has to be conserved, though. Well, if we heated it up, basically, then we pumped it with more energy. It wasn't like we just, voila, they suddenly started going faster. Well, it gets a little confounded. Okay, now, look, I've got two objects over here. Now, the objects are the little balls, the matter, okay? So here we have a pot of boiling water, okay? It's water boils at 212 Fahrenheit. We're going to talk about Fahrenheit and Celsius, okay? It boils at 100 degrees Celsius. And here we have an oven. Those are also water vapor particles, okay? But they're way beyond boiling. They're actually gases, gas particles, okay? So temperature isn't the only thing that says how much kinetic energy an object has, or how much energy an object has. If you read this slide, it says even though this is cooler, okay, it has more energy. Why does this have more energy over here? Because what? Because it's smaller mass. This one over here. I'm going to say this one has, oops, more energy. And actually, I need to kind of change that out. I'm going to call it T for thermal energy. This one has less thermal energy. Now, I think that with regard to mass, what I'm kind of liking is, what do you think, does this have, how would you compare the two masses?
Water.
If they're similar volumes, it's more dense. Yep. This one over here, this one is more dense. That's more, not mine, so more dense. Yeah. So this is more dense, and actually, to me, it's got more mass over here. Okay? More mass in a smaller volume, which makes it more dense. Yep. So when we point to something that says it has that much amount of thermal energy, okay, you have to actually talk about the density and or the mass you have that you're pointing to. All right. So here's our 3 temperature scales. Like I said, if you're like me, one of the things you always have to do is look at the weather. And if you look at the weather, you're probably going to look at Fahrenheit temperatures. Most little weather stations will let you go Fahrenheit or Celsius. Fahrenheit is English, Celsius is metric. And on this slide is kind of some important temperatures. So we said water boils at 212 Fahrenheit, 100 Celsius. Water freezes at 32 Fahrenheit. What does temperatures water freeze at in the Celsius scale? 0, yep. Okay. Now, 2 things. There's a 3rd scale added here, and it is the Kelvin scale. The Kelvin scale is also metric. Kelvin scale and the Celsius scale are both metric. Okay, now, for both of these, though, for all 3 of these scales, what happens to matter as you cool it down? What happens to its motion? It goes more slower and slower and slower. So the Kelvin scale was introduced basically, as far as I can tell, to identify the temperature at which molecular or atomic or motion of matter stops. 0 Kelvin, matter doesn't move anymore. We were kind of talking about this in the review session, but you're like, one of the premises of this universe is that all matter has motion. So how can 0 Kelvin and matter doesn't move, how can they coexist? Okay, well, they don't. And we were kind of talking, and if you Google absolute 0, has anybody ever cooled something down to absolute 0? The answer, as far as I can tell, is no. They've approached it. But 0 Kelvin is what we call absolute zero. There's a test question on your test Friday about that.
So no matter what the
0 Kelvin.
Celsius is, Kelvin is always 273.15 degrees more, right?
Yes. And I'm exactly. So these guys down here, the Kelvin and the Celsius scale, they're both metric. They're just kind of offset by 273.15 units. Yep. So it's kind of nice. They're the same step. They're just off. Now, the whole Fahrenheit, if you've ever tried to convert from Fahrenheit to Celsius, I just Google it. I don't know. Like, I don't know. It's got the whole 9/5 thing, and or the 1.8 and 32. Okay. Okay. Very good. So yeah, kind of like I think maybe Lindsay was saying too. Here at 0 Kelvin, you're looking at a Celsius temperature of negative 273.15. And up at here at 0 Celsius, you're looking at 273.15 Kelvin. That's not. Now I'll tell you. Do we have time? So like I went to the Chicago. Remember, you can get lab credit if you go to Chicago and go to the Adler Theater Planetarium, Adler Planetarium in Chicago. I've been there several times. It's fun to take the train. But anyway, for what's that?
What's it called?
The Adler Planetarium in Chicago. It's really cool, and the train's not bad, like cost-wise, and just go over spring break. Don't forget to take a selfie in front of the planetarium. Make sure it's just packed full of awesome stuff. So when I went there, though, they have like a cool planet exhibit, and so for each planet they have its own little thing, And they would say, well, how cold is the planet? And they would have like negative 300 Celsius is on there, on how a planet is that cold. I mean, it never went down to that. Of course, nothing can go lower than 273.15, but it just bothered me that they had negative 300 Celsius. I'm like, dude, there's nothing between that. So I haven't yet, but I feel like getting Neil deGrasse Tyson involved in this.
Yeah.
Sounds
Why
like,
did they put that then?
yes, he's a museum
What's the
person.
reason behind
Maybe they meant Fahrenheit.
I don't know. No, I took a picture of it, but yeah, they might have meant something else. But this is why we can't get anywhere. Anyway. Okay, those are the 3 temperature scales. So, kind of getting back to kind of the planets thing. Did you guys remember, actually, one of your terms in chapter 1 was galactic recycling, or basically when stars live their lives, they blow up, and then new stars can be born from them. Okay. Well, I think that's where I do it. It's coming in. We'll hold that thought. Okay, so here we have somebody throwing up a ball. What happens to the ball when he releases it? It falls down, yeah. What happens to its speed as it falls? It increases, exactly. 10 meters per each second, 10 meters per second for every second it falls, exactly. Yes. So do you buy this? When it's up here, it has 0 velocity. If it has 0 velocity, how much kinetic energy does it have? None. Yeah, because KE is equal to 1/2 mv squared. If v is 0, KE is 0. No kinetic energy if it's stopped. Okay, and it's going to go fastest down here. So here it has, just before it splats the ground, it's got its fastest speed, so it has its most kinetic energy, right? So here's how this goes. Potential energy, I'll go ahead and put this up here. PE is the abbreviation for potential energy. That's a B. PE, potential energy, is equal to mass times the gravitational constant times how high that object is. All right, potential energy. 0 velocity, but what do you think about its height? Is it the highest it is going to be if it's going to start falling next? Yeah, the height is at its maximum, so it's at its maximum potential energy here. So maximum potential energy, no kinetic energy. What happens about its potential energy when it's fallen halfway? So now how big is your H? Half of that. So your potential energy is decreased, but it's going faster, so your kinetic energy has increased. So that sort of trade-off, just kind of in this simple example, is kind of showing you the trade-off between getting less potential energy but getting more kinetic energy. Okay, that's just kind of showing you the trade-off of how, in this case, potential energy is, kinetic energy, I guess it would be potential energy converted to kinetic energy, final answer. Yep. So now this is back to the galactic recycling thing. This again is kind of showing you how potential energy is converted into kinetic energy. So this little gray thing could be the cloud. We're going to call clouds coming up here in astronomy, we're going to call them nebula. Nebula. So this is our little nebula that's going to become a star. And actually over here, this orangey looking thing, okay, is kind of the beginnings of our star. It's so exciting. Okay, so a couple of things there. Let me put the rest of this up here. Oops. Ooh, goodness. Okay, so a couple of things up there. Which one's hotter? Can you just tell from this figure? Is it the cloud or is it the little baby star?
Little baby star.
Little baby star is hotter. Okay, if it's hotter, that means the matter in there is moving faster. So actually, it increased in kinetic energy. So we have basically kind of, in no pun intended, a vacuum. Basically, we've got more kinetic energy going there. It didn't just happen. It came from actually potential energy being decreased. So here we go. Here's my nebula, okay? It has a lot of potential energy here, okay? As it gets smaller, it has less potential energy. That potential energy is converted to kinetic energy. That kinetic energy is heat, okay? So that kinetic energy actually is important in that little baby star being born, okay? Now we're going to have to talk, if you're like me, you're like, well, why does this start? You have a nebula, why does it start to contract? Like, well, gravity, right? But there's actually going to have to be some sort of stimulus to make this sort of thing start to begin to contract. And there's a couple different ways to get that started. But if you can get something like this, make it smaller, okay, you're decreasing potential energy, increasing kinetic energy. And one form of kinetic energy is kind of this temperature thing we got going on in stars. And one thing about stars is it has to get hot enough to begin nuclear fusion in the center of that star. So it's kind of a critical temperature that has to happen.
Could that happen to Jupiter?
Jupiter, I think I read, I think it needed to be, it was close. Jupiter, if it had been maybe 5 times more massive, I'm not sure. If it had been 5 times more massive, it actually would have converted enough potential energy into kinetic energy, be hot enough to become another star. And actually, when we look at stars, I love this part too. When you look at stars, very few of them are alone. There are many stars, most stars actually have a companion star. So they were actually born out of the same nebula, and they just got 2 stars out of it. Yeah, so.
That'd be really different if it would have been.
Yes, it would be very different. Is it a Star Trek movie where the planet has 2 suns? Or so.
Star Wars? Tatooine?
Yeah, or is it 2 moons?
2 suns.
2 suns, yeah. So actually you could have a planet kind of having 2 suns, which is kind of weird. That one hurts my mind. Okay, what else? Oh, we got the blow-up one. Okay, so I said conservation, right? Energy is conserved, okay, and matter is conserved. But here, and we don't do it very often, but actually energy and matter can be converted back and forth. Like, are you serious? Yeah. And so, of course, you see the picture of this mushroom cloud, okay, and this is some sort of nuclear reaction, okay, nuclear bomb. And the thing that happens with in a nuclear reaction is a very small amount of matter is converted into a large amount of energy in a nuclear reaction. I said a minute ago that stars need to be hot enough to have nuclear reactions going in the core. So our sun, bless you, our sun is actually taking some of its mass and converting it to energy. That's what our sun is doing. Anytime you have a nuclear reaction going on. Now there's a couple different types of nuclear reactions. Our sun is actually taking hydrogen, squishing them together, okay, making helium, and losing a little bit of matter and creating a lot of energy. Anybody know what the C is in E is equal to mc squared? Anybody?
Speed of light.
It is the speed of light, yes. It's like 186,000 kilometers per second. It's a big number, and you square it. So this is just to say the whole c squared is a humongous number, so if you take a little bit of mass times a humongous number, you get a humongous amount of energy. Okay, so that's the kind of nuclear fusion thing. Clear at the end of the course, be here before you know it, June or April, okay? We're going to be talking about the Big Bang, and the Big Bang did the opposite. The Big Bang took a lot of energy, because actually the whole thing that started the Big Bang was pure energy, and it converted a lot of energy into a little bit of mass. Or, yeah, that's right, matter, mass. So it did just the opposite. So it's conserved, but actually Einstein's pretty with it, and this E is equal to mc squared thing is going back and forth. I think it's cool. Are we getting close? Oh, okay. All right. So let's see. We had Kepler's 3 laws. Now Kepler's 3 laws are all about planets. And then we had Newton's 3 laws of motion. Okay. Now we have Newton again, who actually came up with an equation talking about gravity. And I think I've already said gravity, although gravity, we're all kind of like, oh yeah, I dropped my pen and it falls to the floor because of gravity. Like, I got that. But it's kind of like, really? I mean, what is the thing within matter that makes that happen? And so, what scientists do to understand things like that is basically look at what matter is. And like, oh, I know what matter is. I know an atom. Well, what they do is they take an atom and they break it down into teeny weeny parts using what we call a particle collider. Okay, so anyway, so they're still looking into the whole gravity thing. But anyway, so Newton saw that actually the force of gravity, okay, we have an equation up here, is equal to, in the top we'll put m1, m2, that's the masses of the two objects that are going to have a gravitational force between them, okay? In the bottom we have d squared, that's the distance between them. Okay, m1, m2 masses, d squared, the distance between them. Now, the g, the capital G, actually, you'd have to look it up. It's a constant, okay? And sometimes people will tease that for this universe, it has one constant. For another universe, the g might have a different constant. Okay, but it's just basically a number that says that m1, m2, and d squared is always related to force of gravity this way. So I think on your test, and if you listen to the review video, you're going to catch this. I say something about what would happen what happens to the force. You guys are doing pretty good with these equations. What happens to the force if we increase m1? It goes up. Yeah, increase m1, force goes up. Exactly. And it kind of, even if you didn't have the equation, you're like, hey, if something's more massive, like the Earth versus the Moon, okay, something's more massive, it's going to have a stronger force of gravity. Exactly.
So will we plug like Earth into M1 and like the Moon into M2?
Right. Yes, and he said, well, so if we were looking at the tug between the Earth and the Moon, would M1 be the mass of the Earth and M2 be the mass of the gravity, mass of the Moon? That would be right. And kind of along those lines, if you're just looking at the gravitational attraction of us peoples with the Earth, you can make M1 the mass of the Earth and M2 the mass of us, one person. And it seems a little lopsided there, but okay. And then the D part, okay, would actually be, and we'll talk about this when we talk about like white dwarfs and black holes, but the D part would be where you are to the center of your mass. So it's like us to the center of the Earth, which there are no dinosaurs there. Okay.
So D is the distance.
D is the distance, yep. So what happens if you increase the distance? What happens to the force? It gets weaker, yeah. And we were kind of talking about this with like the Coulombic force of between something that's positive and negative. It's kind of similar too. Well, just to kind of finish up then, Newton must have lived on the coast. Oh, wait a minute. You guys don't have this one, do you? Yes, you do.
Yeah.
Okay. I kind of talked a little bit about this when I said the International Space Station, if it wants to go ahead and insert itself into orbit, it needs to have, but then I kind of messed that up, didn't I? If it wants to, is the International Space Station, is it still under the influence of Earth's gravity? Yes, hopefully. Okay. If it wanted to escape Earth's gravity, it could go straight up with a particular velocity. That's called the escape velocity. And one of the things when we talk about black holes is we're going to see the escape velocity, how fast you need to go, is actually faster than the speed of light. So that's the problem there. What if you were on the moon? Would the escape velocity be higher or less than if you're on Earth? It would be less, exactly. Escape velocity is kind of a function of the mass and how that mass is distributed. Yeah, you got it. Okay, do you have a question?
Yep. So when you said that they go up, do they not go up straight into when they go out in outer space and orbit, they don't go straight up to do the orbiting?
Yeah, well, they go straight up and then they eventually kind of get, they get to their, you're fine, because I'm kind of thinking how that works. I think they get to a particular altitude, and there's where they start their movement that way. That's what I'm thinking. And they insert themselves at the elevation that they want. Yeah. Mm-hmm. Yeah. So this is where I said I think Newton lived near an ocean, but I'm not sure. He must have. England? Yeah. It's the island across the pond. Yep. So, and I've never lived near on an ocean, but if you have, you know about this tide thing. You know, these large bodies of water, like the Pacific Ocean, will go out. It will recede, and from the coast, okay, at low tide, and then it will come up. We call that high tide. And the reason is basically the large bodies of water. Somebody said, does tides work with the Mississippi River? And I don't think so. But if the body of water is large enough, basically the gravity of the moon's pull will suck it up, okay, and kind of towards the moon, okay? Is that not cooler? It really, okay? So right now the sun's over there and we're just past kind of new moon, and the moon is kind of going hopefully on its left, okay? Moon's over there. I looked. One of these days we'll have to look at the moon in the daytime. But so basically the moon's there, so the water is being pulled up there, okay? Now the earth will spin, okay, and the moon will kind of look like it goes across the sky, and then this bulge will follow the moon. We'll go this way, and the bulge of water will follow the moon. That is so cool.
Isn't the high tide on both sides?
Exactly. That's what this is showing. So you have a high tide where the moon is, and on the back side you have another high tide. So
And it's like level in the middle.
yeah, it's flat. It's low tide in the middle, high, two lows. And so how long does it take the Earth to spin once? How many hours? 24 hours. So you have a high tide here. You have a high tide 12 hours from here. Okay? So you have high tide, 6 hours low, 12 hours high, 18 hours low, another complete the circle high, relatively speaking. Now remember the moon is a moving target because the moon is orbiting the Earth. So that high tide kind of goes like that. Is that not cool? I just think that's neat. Okay, one other thing, and actually there is a test question on this last slide about this. So you kind of see the bulges, right? You kind of see the up there. So high tide is where the moon is. Now, if the sun, and the sun is over here on the left, if the sun is in line with the moon, okay, and by in line, I mean it could be at new moon, where you have Earth, moon, sun, or it could be full moon, where you have moon, Earth, sun. Oh, I said that right, but anyway. Can you see where they're lined up, the moon and the sun, either one? Basically, they work together, and the sun gives an extra push to that pull. Get push to that pull? Anyway, they're extra high tides. They're called spring tides. Now, if the sun is not in line, but at a right angle to the location of the moon, you're still going to have high tides, but your high tides are going to be kind of diminished, and we call those neap tides. Okay, those are called neap tides. So you'll still have high tide, but it's kind of like a. And somebody was asking this morning, what if, we talked about sometimes the moon's close at perigee and sometimes the moon's farther away at apogee. What if you have a full moon at perigee? What does that do to your tides? And actually that can make even, because the distance is cut, even stronger tides, spring tides. Okay? Phew! Right, well that is unit 1, okay? So any questions about anything?